So number 59, we have a 2.65 kilogram power line running between two towers that have a length of 38 meters and is under a tension of 12.5 newtons. A, what's the speed of a transverse wave pulse set up in the line? This one pretty much plug and chug. If you remember the equation for the velocity of a wave inside of a string or rod, it's equal to the square root of the tension over mu. And you might say, whoa, wait a second, what's mu? Well, mu is the mass per unit length. In this case, we know the mass of the wire is 2.65 kilograms, and its length is 38 meters. And so we can figure out mu is 0.0697 kilograms per meter. Plugging in our numbers, the tension's 12.5, mu is the number we just found. We discovered the velocity is about 13.4 meters per second. Not too terrible, but part B is the more interesting one. And the key on this one is, if the tension in the line was unknown, describe the procedure a worker on the ground might use to estimate the tension. Now, if they're up on top, they can just pluck it and measure the velocity or the time it would take a pulse to go from one side to the other. But in this case, if you're standing on the ground, how would you solve this? Well, again, remember, you do know the distance between these two poles is roughly 38 meters, the length of the wire. What could a worker do on the ground? Well, they'd have to just observe, unless they had a really tall pole that they could strike the wire with and measure the velocity. What they could do is a trick like this. Please realize, if we know velocity, you could actually figure out the tension if we know mu. And I'm assuming here they must know mu. Otherwise, you wouldn't be able to find the tension. Well, if we use this equation, we could solve for the velocity, which we could then plug in here and go work backwards and solve for the tension. But how do we figure out the frequency and the wavelength? Well, frequency you could measure. It's possible that the wire could be swinging back and forth between the two poles. Again, imagine one pole being here and the other pole being here. It could be swinging back and forth this way, or it could possibly be swinging back and forth this way. These are probably the two most common ways it could be oscillating. There are others, but let's assume there's at least a light wind blowing that day, and the worker on the ground can see whether it's oscillating that way or that way. Well, what does that give us? Well, if you look at this at any given instant, please realize that this would be one complete oscillation. In other words, this distance right here would be the wavelength. So that's pretty nice. So in this case, what does that mean? That means the wavelength of the oscillation in the thing would be equal to the distance between the two poles, or 38 meters. In the first case, that's only half of a complete wave. So in this case, the wavelength would be 76 meters. So first of all, you could figure out the wavelength by figuring out which way it's oscillating, if you know the distance between the poles. And then you could actually time the frequency. You could measure how many oscillations the wire is making per second. Once you know the wavelength and the frequency, you can, of course, calculate velocity using this equation. If we know velocity, we can, of course, use this equation now, assuming we know mu, we know velocity, and yeah, sure enough, you could calculate the tension. This is one possible way of doing it amongst many other ones. Hopefully this helps.